So, in the last class we were discussing about propagation constant, that is gamma, which is a complex quantity given by alpha plus j beta. Okay, so gamma is propagation constant, that is equal to alpha plus j beta, where alpha is attenuation constant and beta is phase constant. Then the values given by gamma is square root of j omega mu into sigma plus j omega epsilon. You know that epsilon is permittivity, mu is permeability, omega is angular frequency, and sigma is conductivity. So all these terms are quite familiar now. Okay, so this is propagation constant, square root of j omega mu into sigma plus j omega epsilon. Okay, and we solved it and we got alpha and beta values. These equations are important. Only difference is here it is minus and here it is plus. So alpha beta values are omega square root of mu epsilon by 2 into square root of 1 plus sigma by omega epsilon the whole square minus or plus 1. Minus 1 in case of alpha and plus 1 in case of beta. So these are the main equations. And now what we assume is the wave is propagating in z direction, okay, and electric field is in x direction. So this Exs will be a function of z, as wave is propagating in only one direction, that is z. So it is a function of z and its direction is x. Electric field has only one component, that is it has only x component. So electric field direction is in x direction. Wave is propagating in z direction. So the function is, this is a function of z as it is propagating in z direction. So let's assume the phasor form of electric field as Es is equal to Exs z Ax, where Ax is the unit vector in x direction. And this was the main vector wave equation or Helmholtz equation, del square, which we derived in the last video. So del square Es minus gamma square Es is equal to 0, or del square minus gamma square into Exs z. Okay, so this is the equation, and here we know that Exs is a function of z. So dou x square, dou by dou x square and dou by dou y square will be 0. So we can write it like this: dou square Exs z by dou z square. So del square modified to dou square by dou z square minus gamma square Exs z is equal to 0. And we write the equation like this. Why? Because electric field is in x direction and wave is propagating in z direction. E has only x component and it is a function of z only. It is not varying with respect to x or y. So dou by dou square, dou x square and dou square by dou y square, both components are 0. This is a scalar wave equation. Okay, and now we have to solve this equation. To solve, we solve this second order differential equation, and like this: d square by dz square minus gamma square Exs z is equal to 0. And we get the equation like this: Exs z is equal to E0 e raised to minus gamma z plus E0 dash e raised to gamma z. This means that this part is a wave that is traveling in positive z direction, and this is a wave that is traveling in negative z direction. In the last video also I explained e raised to minus gamma z shows positive traveling wave in z direction, and e raised to gamma z shows a negative traveling wave in z direction. So this negative sign shows that it is in positive direction. Positive sign shows that it is in negative direction. So we write it as two parts. Okay, so we can write like electric field is the real part of this, or real part of E naught, which is the highest amplitude, E naught e raised to minus alpha z. We are splitting gamma into alpha plus j beta. Okay, so you write like this, and also this is only the according to the phasor form, this is only function of space derivatives or xyz components. So in addition to that, there is a time dependence factor that will be e raised to j omega t. So exsz into e raised to j omega t, that is a total equation for electric field vector. So then when you take the real part, you will find that e raised to j theta, the real part is cos component. So you write like E0 into e raised to minus alpha z into cos omega t minus beta z, because it is alpha here. What you write is minus alpha minus j beta. So like that you write Ez component is E0 e raised to minus alpha z into cos omega t minus beta z. This means that the wave is traveling in positive z direction and the electric field is in x direction. Similarly, you can also get the equation for magnetic field vector like this. Real part of h0 e raised to minus alpha z into e raised to j into omega t minus beta z ay. Okay. So, in short, you can understand that both electric field and magnetic field are perpendicular to each other in a transverse electromagnetic wave, and both these fields are perpendicular to the direction of propagation of the wave. So in this case, you know that E in x direction, H in y direction, and propagation of wave in z direction. Okay, so this is the general equation for the wave. Ez t is E0 e raised to minus alpha z into cos omega t minus beta z into unit vector Ax. And in another term, which is intrinsic impedance, that is given by eta is equal to E0 by H0. Okay. So what we learned is, just learn these parts, how to the general form of electric field and magnetic field, because for all the problems we get the equation like this, and from the equation format we take the values of alpha, omega, beta, E naught, etc. Okay, so you have to note these two equations, the form of electric field and magnetic field equations, and intrinsic impedance is given by E0 by H0. And now what we learned earlier itself, TEM waves or transverse electromagnetic wave, that means electric field and magnetic field are perpendicular to each other, and both these fields are perpendicular to direction of propagation of the wave. So A is the unit vector in electric field direction, H is the unit vector in magnetic field direction, and AK is the unit vector in the direction of propagation. Then AK is equal to AE cross AH. Okay. And now attenuation constant. So you know that gamma is equal to alpha plus j beta, where alpha is the attenuation constant. Okay. It is a measure of the spatial rate of decay of the wave in the medium. Attenuation or rate of decay is given by attenuation constant or attenuation coefficient. It is given by the value alpha. So positive traveling wave, this is the format, E0 e raised to minus alpha z into cos omega t minus beta z into unit vector Ax. Okay. And now coming to phase constant. Phase constant is the measure of phase shift per unit length, and the unit is radians per meter, and unit of attenuation constant is Nepper per meter. Nepper per meter is the unit of attenuation constant alpha, and unit of phase constant beta is radians per meter. Okay, and beta, the equation is 2 pi by lambda. So it is also called wave number, 2 pi by wavelength. So it's also called wave number, phase constant. Now intrinsic impedance, this is the equation. Eta is given by square root of j omega mu divided by sigma plus j omega epsilon. You might be remembering the equation for eta. Eta is given by, what is the equation for eta? Eta, this is the equation. Okay. Okay, this is the equation for eta. And gamma is similar. Propagation constant gamma is equal to square root of j omega mu into sigma plus j omega epsilon. This is the equation for gamma, which is propagation constant. So compare these two equations. This term and this term is same in both. This is intrinsic impedance. Okay. So this is intrinsic impedance. Here it is j omega mu divided by sigma plus j omega epsilon. Gamma, it is square root of j omega mu into sigma plus j omega epsilon. So you have to compare and learn these two equations. Okay. And this eta, it's a complex quantity like alpha itself, and here the angle is given by tan 2 theta eta equals sigma by omega epsilon. So theta eta will be 1 by 2 into tan inverse sigma by omega epsilon. Okay. So that angle will be between 0 to 45. Okay, because value from 0 to infinity means angle will be 0 to 90, and here it is half into tan inverse, so it will be 0 to 45 degree. Okay. And you know that the equation connecting E0 and H0 is E0 by H0 is eta. So H0 will be E0 by eta. E0 by eta into e raised to minus alpha z into cos omega t. Here you are dividing by eta, so angle you have to subtract. So cos omega t minus beta z minus theta eta into unit vector ay. This is all under the assumption that electric field is in x direction and magnetic field is in y direction, and direction of propagation is in z direction. Okay. That in that assumption only we write all the general equations. So here what you can understand is electric field is leading magnetic field, or magnetic field is lagging electric field by an angle theta eta. Okay, so E and H are out of phase by an angle of theta eta. Okay, and theta eta is given by theta eta is given by 1 by 2 into tan inverse sigma by omega epsilon. Okay, theta it is half into tan inverse sigma by omega epsilon. Here E leads H by theta eta, or H lags E. You know E and H, right? E is electric field intensity and H is magnetic field intensity. H lags E by theta eta. And theta eta is given by this equation, half into tan inverse sigma by omega epsilon. Okay. Now Loss tangent, tan theta. Okay, so tan theta is given by sigma by omega epsilon. It is a ratio of magnitude of conduction current density to displacement current density. So you know that J, current density is sigma E. So conduction current density is sigma ES and displacement current density is J omega epsilon ES. That we already know in when we derived fourth Maxwell's equation, right? Conduction current density and displacement current density. Conduction current density is sigma E. J is equal to sigma E. I think you have learned it in SSD. J is equal to sigma E. So conduction current density is given by sigma E and displacement current density is given by J omega epsilon E. Okay, and E in phasor form you write it as ES. So on dividing you get sigma divided by omega epsilon, because J, when you take the magnitude, J will go out. Also it is sigma by omega epsilon, that is equal to tan theta, and this tan theta is called Loss tangent. Okay, and you know about tan 2 theta eta. Tan 2 theta eta was sigma by omega epsilon, right? So what you can understand, you can understand that this Loss tangent tan theta is equal to tan 2 theta eta. Both are equal to sigma by omega epsilon. So you can write Loss tangent theta is equal to 2 theta eta, where theta eta is the angle, intrinsic impedance angle. Okay, this equation is also important. And tan theta is called Loss tangent. Okay, and this theta is called Loss angle. This is called Loss angle. Okay, so these two terms you should know. Theta is Loss angle and tan theta is Loss tangent. And tan theta or Loss tangent value is tan theta is sigma by omega epsilon, and that is equivalent to tan 2 theta eta. And you can, from this you can understand that Loss angle theta is equal to 2 into intrinsic impedance angle theta eta. Okay, this is not theta into eta. Okay, this is intrinsic impedance angle theta suffix eta, theta eta. Okay, now what is the significance of Loss tangent or Loss angle? Okay, so this value determines how lossy a medium is. Okay, how lossy, that means how much loss occurs in a medium, that is called lossy. And a lossy dielectric means when an electromagnetic wave propagates through a medium, some power is lost due to the imperfect dielectric. So dielectric is expected to have no loss at all. But when some loss is there, that means when an electromagnetic wave travels through the dielectric, some power is lost. So that loss is given by, that loss can be measured by using Loss tangent or Loss angle. Okay. So that is the significance of this value. So medium is good dielectric. Good dielectric means loss should be less. That means sigma is conductivity. Sigma should be much less than omega epsilon. If that be the case, we say that the medium is a good dielectric. It is lossless or almost perfect. If sigma 0, you can say that it's a perfect dielectric, or loss is almost 0 if sigma is 0. But if it's a good conductor, sigma will be very high. That means sigma will be much greater than omega epsilon. And you know that this Loss tangent is given by tan theta is equal to sigma by omega epsilon. So based on that, tan theta is sigma by omega epsilon. So sigma much high means tan theta will be very high. So if Loss tangent is very high, medium is a good conductor. And if Loss tangent is very small, the medium will be a good dielectric. So now we can just conclude. So all these general things which studied is in when we consider a lossy dielectric. And you know the equation for propagation constant. Propagation constant gamma is alpha plus j beta, and equation for gamma, this is just a revision of all we learned till now. So gamma is equal to alpha plus j beta, and gamma, the value is j omega mu into sigma plus j omega epsilon. Okay. So you are familiar with all these terms. Sigma, that is this is sigma. This is propagation constant, mu permeability, sigma conductivity, and epsilon is permittivity. This omega is angular frequency. Okay. Then these are the equations we learned. Equation for alpha. What is alpha? Alpha is attenuation constant. Attenuation constant, that is given by alpha. And the unit is very important, Nepper per meter. When you do problems, unit you must write. Attenuation constant, alpha is Nepper per meter unit, and beta, that is phase constant. So phase constant is beta, and the unit is radians per meter. Okay, and it's beta. And equation is very important. So here also you can see this term sigma by omega epsilon. So this term has so much importance, sigma by omega epsilon. So tan 2 theta, this is equal to sigma by omega epsilon. This is also equal to tan theta, which is Loss tangent, which we learned now. So Loss tangent is tan theta, that is equivalent to tan 2 theta eta. This is also equal to sigma by omega epsilon. Then intrinsic impedance equation is square root of j omega mu divided by sigma plus j omega epsilon. And when you multiply these two terms and take the square root, you get propagation constant. So you compare and learn those two equations. Then velocity of the wave in a particular medium is given by u, that is omega by beta, which is equal to 1 by square root of mu epsilon. So velocity of wave in a medium is given by 1 divided by square root of mu epsilon. 1 divided by square root of mu epsilon. And you know that permeability mu is equal to mu 0 mu r, and permittivity epsilon is equal to epsilon 0 epsilon r. Here this mu r is relative permeability and epsilon r is relative permittivity. This is permeability in free space and this is permittivity in free space. Okay. So in the last class we discussed the various values, propagation constant, alpha, beta, etc. in case of a lossy dielectric, if the waves are propagating in a lossy dielectric. So gamma, the equation for gamma is square root of j omega mu into sigma plus j omega epsilon. So that was the equation for gamma, and you know that gamma is equal to alpha plus j beta. So from that you got these two equations. Alpha is equal to omega square root of mu epsilon by 2 into square root of 1 plus sigma by omega epsilon the whole square minus or plus 1 in case of alpha and beta. Okay, these were the general equations. And lossy dielectric means it is a medium in which an electromagnetic wave propagates and it loses power. Some power will be lost, and that is due to this imperfect dielectric. If it is a perfect dielectric, there will not be any loss, or conductivity will be almost equal to 0. There is absolutely no conductivity in case of a lossless dielectric. But in case of lossy dielectric, there will be some conductivity, and because of that there will be some power loss for the electromagnetic wave when it propagates through that medium. And the next thing was intrinsic impedance eta, which is a complex quantity that is given by square root of j omega mu divided by sigma plus j omega epsilon. Then we learned tan 2 theta eta. Theta eta is the angle of intrinsic impedance. E leads H or H lags E by an angle theta eta. It is given by, theta eta is given by 1 by 2 tan inverse sigma by omega epsilon. Okay. So all these were the equations. Now we will move on to the different cases. So first case is lossless dielectric. So we know that lossless dielectric means the ideal case, there won't be any conductivity for that dielectric. If that be the case, sigma will be much less than omega epsilon, or sigma will be almost equal to 0. You can equate it almost equal to 0 in case of lossless dielectric. And being a dielectric, you cannot assume that it is its permittivity and permeability as mu 0 or epsilon 0. There will be a relative permittivity epsilon r and relative permeability mu r. So epsilon is epsilon naught epsilon r and mu will be mu naught mu r. Conductivity will be 0. This is the important thing you should note. So what will be equation for alpha and beta? We know that the equation for alpha is alpha or beta. Both alpha beta will be equal to, what is the equation? Omega square root of mu epsilon by 2 into square root of 1 plus sigma by omega epsilon the whole square minus or plus 1. This will be the equation for alpha and beta. So if this be the case, sigma you can take it as 0. Okay, so this term will be 1. So if that is 1, then it will be, in case of alpha, it will be omega square root of mu epsilon by 2 into 1 minus 1, that will be equal to 0. So it will be equal to 0. Alpha will be equal to 0. Again beta will be omega square root of mu epsilon by 2 into 1 plus 1. So that will be 2. Beta, in beta it will be plus. So 1 plus 1, here it is 2. In alpha it is 1 minus 1, it will be 0. So here you can get beta is equal to omega square root of mu epsilon. You know that 1 by mu epsilon is V. So this can be written as omega by V. That's how you get beta is equal to omega by V. This is one equation, right? So here in this case, you understand omega square root of mu epsilon. So these are the two equations. These are very important. And this is valid only in which case? In case of a lossless dielectric. In the normal case, we can't equate like this. But in case of lossless dielectric, when sigma is equal to 0, when conductivity is equal to 0, you can take the lossless dielectric, conductivity is 0 and alpha attenuation will be equal to 0. Because why attenuation is happening? Attenuation means power loss of the electromagnetic wave. So attenuation happens because the dielectric is not perfect or there is some loss in the dielectric. So if it is completely lossless, that means attenuation will be 0. There will be no attenuation if wave propagates in a lossless dielectric. Then beta, phase constant, is equal to omega square root of mu epsilon. Mu value and epsilon value is mu naught mu r and epsilon value will be epsilon naught epsilon r. Okay, so then next we'll take this. See, this we already know. Use beta is equal to omega square root of mu epsilon. Then another general equation, beta given by 2 pi by lambda or lambda is 2 pi by beta. Then comes the equation for intrinsic impedance eta. Okay, what is the equation for eta? Intrinsic impedance eta will be square root of j omega mu divided by sigma plus j omega epsilon. So here in lossless dielectric, what happens? Sigma will be equal to 0. So this can be written as square root of j omega mu divided by j omega epsilon. So it will be square root of mu by epsilon, and this is a complete real quantity, right? There is nothing, the imaginary part is 0. So you can write theta eta as 0. So E and H, E leads H by angle theta eta. So this means they are in phase. They are in phase in case of lossless dielectric. Lossless dielectric in the case le idu varu. Only in case of lossless dielectric, E and H are in phase because theta eta is 0. Intrinsic impedance value eta will be square root of mu by epsilon. Okay. Now next case, that is we are assuming the plane wave to be in free space. Free space means the first thing to be noted is conductivity is 0. Sigma will be 0. There is no loss. That is one thing you should know. Then in free space, the relative permittivity and relative permeability are equal to 1. Both are 1. So epsilon will be epsilon naught and mu will be equal to mu naught. So these three things we should remember when dealing with free space. So again sigma is 0 in last case. In when we discussed that lossless dielectric also, sigma was equal to 0. The same thing will be applicable here also. In last case what we learned, alpha will be equal to 0 and beta will be equal to omega square root of mu epsilon. Why this happens? Because sigma is equal to 0. So this will be same in this case also. Alpha will be 0 and here beta, what will be the value? Omega square root of mu naught epsilon naught. Why? Because mu r is equal to epsilon r is equal to 1 in free space. Okay, So velocity in free space is c. That will be equal to 1 divided by square root of mu naught epsilon. This is equal to 3 into 10 raised to 8 meter per second. This you should remember. Okay. So in this case you can write omega by c, where c is equal to 3 into 10 raised to 8 meter per second. Is it clear? Omega by c, that is c is velocity in free space, that is 3 into 10 raised to 8 meter per second. And based on this, we can discuss one more thing, is the normal velocity of wave in a medium. Velocity of wave in a medium. What will be the velocity of wave in a medium? V is given by 1 divided by square root of mu epsilon. Okay, that will be equal to 1 by square root of mu naught epsilon naught into mu r epsilon r. This will be the general velocity. Okay, this will be c divided by square root of mu r epsilon r. This is an important equation. Okay, velocity in a medium is given by c divided by square root of mu r epsilon r. Okay, where V is equal to c divided by mu r epsilon r, where c value is 3 into 10 raised to 8 meter per second. All these are important equations. You should go through it again and again and learn it well. Okay. Okay, then coming to intrinsic impedance, we know that when sigma is equal to 0, what happens? Eta will be square root of j omega mu divided by sigma is 0. So j omega epsilon, and you got the value as square root of mu by epsilon. E and H are in phase. So this much we learned earlier itself. This is applicable here also, and here in free space you can write it as eta naught, representing that it is intrinsic impedance in free space, that is equal to square root of mu naught by epsilon 0, because relative permittivity is 1 in free space. These values are constant. You know that mu naught is a constant value, epsilon naught is a constant value, and on substituting these two values you get 120 pi or 377 ohm. Unit of intrinsic impedance is always ohm. Ohm is the unit. So in free space, intrinsic impedance is a constant value square root of mu naught by epsilon 0, and that value is equal to 120 pi or 377 ohm. You can use the equations based on the problem. If there is like other quantities are with pi, you can substitute 120 pi. Okay, otherwise you can substitute the final value 377 ohm. So this is the value of intrinsic impedance in free space. Okay. And now you can see that, let's assume that always the common assumption that we make is the propagation is in z direction. Wave is propagating in z direction. Electric field is in x direction and magnetic field is in y direction. So this is our assumption. So based on this assumption, we take that electric field in x direction, magnetic field in y direction and propagation in z direction. This is how we call it as transverse electromagnetic wave. Transverse electromagnetic wave means electric field and magnetic field are perpendicular to each other, and it is perpendicular to the direction of propagation of the wave. So with that assumption, how you can write E is equal to E naught cos omega t minus beta z into unit vector Ax, and H you can write as H0 cos omega t minus beta z. In addition to that, here one more thing comes, minus theta eta, because H lags E by an angle theta eta. But here as it is equal to 0, as theta eta is equal to 0, how we write? We write the same way, H0 cos omega t minus beta z, because E and H are in phase. And H0 will be equal to E0 by eta naught. So this is how you write the equation for electric field and magnetic field. Now we'll take the last case. So first, in the general case, we learned how plane wave propagates in a lossy dielectric. Lossy dielectric is the general case and we derived all the general equations. Then comes the first case in case of lossless dielectric. Then we discussed how the plane wave propagates in free space, and this is the last case, that is how plane wave behaves in good conductors. Okay. In case of lossless dielectric and free space, we take sigma or conductivity as 0. But in case of good conductor, how it will behave? Conductivity will be very high. It will be almost equal to infinity. Conductivity will be almost equal to infinity. So first thing is we are going to calculate the value for alpha and beta. Okay. Alpha beta value is, what is the equation for alpha and beta? It will be omega square root of mu epsilon by 2 into square root of 1 plus sigma by omega epsilon the whole square minus or plus 1. So this is the equation. Earlier this was 0, but here this is a very high value, almost equal to infinity. So because of that, you can neglect this 1. So square root of sigma by omega epsilon the whole square. So square root and square, it will get cancelled. So it will be sigma by omega epsilon. Again it is a high value, so this minus or plus 1 can again be eliminated. So you will get alpha is equal to beta, that is equal to omega into square root of mu epsilon by 2 into this whole term will be reduced to sigma by omega epsilon. Why? Because sigma by omega epsilon is a very high quantity. So here 1 is eliminated and square root of a square term means that term itself. So again sigma by omega epsilon comes here. Again minus or plus 1, that value is very small compared to this high value. So you take this whole value in the bracket as sigma by omega epsilon. Now you can cut it, epsilon get cancelled and you get omega into square root of mu sigma by 2 omega. Okay, again omega is taken inside this omega mu sigma by 2. Omega square, this when this is taken inside the square root, omega square comes and omega square get cancelled. So this is the value. You will get alpha, beta both as equal and that will be equal to omega mu sigma by 2. Again omega value, what is the value of omega? It is 2 pi f. On substituting here you get square root of pi f mu sigma. Here f is frequency, mu is permeability and sigma is conductivity. Okay, now you got the value for alpha and beta. Here in case of good conductors, attenuation constant is equal to phase constant, that is equal to square root of pi f mu sigma. Okay, this is an important equation. This is applicable only in case of good conductors. Only in case of good conductors. And now trying to find the velocity. Again u is equal to omega by beta. This is a general equation. And here you get beta value. Alpha beta is equal to, what did you get? It's equal in terms of omega, you can write square root of omega mu sigma by 2. Square root of omega mu sigma by 2. Okay, so again you can write square root of 2 omega by mu sigma. This is what you get here. Okay, you'll get like this. Then again lambda is 2 pi by beta or beta is equal to 2 pi by lambda. This is again the general equation. Now comes eta. Intrinsic impedance, the general equation is square root of j omega mu divided by sigma plus j omega epsilon. But here what happens? Sigma is a very high value compared to this value. So we can neglect this and you can write it as square root of j omega mu divided by sigma. So this is the equation. Square root of j omega mu by sigma, and square root of j omega mu by sigma means you have to calculate theta eta. A completely imaginary quantity means that is 90 degree and square root means half of 90. That means 45 degree. So in case of a good conductor, theta eta will be 45 degree. And what is the significance of theta eta? E leads H by 45 degree or H lags E by 45 degree. So this you should remember, E leads H or H lags E by 45 degree. This is applicable only in case of good conductors. Okay. So here if you just assume to write the equation, how we can write vector E is equal to E naught cos omega t minus beta z. As it is propagating in positive z direction, you can write omega t minus beta z into unit vector Ax, because we assume electric field in x direction. Then what about H? Vector H will be H naught cos omega t minus beta z minus 45 degree. So that will be pi by 4 into unit vector Ay. And E naught by H naught will be equal to eta. Eta is this ratio of electric field intensity by magnetic field intensity. So you should remember all these things. Now another term called skin depth. Okay, skin depth means it is a measure of depth to which an electromagnetic wave can penetrate the medium. This is a very important topic, skin depth, because skin depth gives the measure or the measure of the depth up to which a wave can penetrate. Because if we take like this, e raised to minus alpha delta as e raised to minus 1, and you are trying to calculate the value of delta. Okay. And you get, when you calculate like this, what you will get, alpha delta is equal to 1 and delta will be equal to 1 by alpha. You will get like this. Okay. So skin depth is given by this equation delta, which is given by 1 by alpha. And you know that in case of conductor, the equation for alpha is, earlier we learned it. What was it? We learned the alpha value as square root of pi f mu sigma. We got like this. So based on that, you can write 1 by alpha is 1 by square root of pi f mu sigma. This is a very important equation. This is the equation for skin depth. This is the equation for skin depth. Skin depth delta is given by 1 by alpha, that is equal to 1 divided by square root of pi f mu sigma. And this means that delta is inversely proportional to square root of frequency. Okay, frequency goes on increasing, skin depth will goes on decreasing. As frequency increases, skin depth will go on decreasing. So skin depth is what is the significance of skin depth? It gives the measure of depth to which an electromagnetic wave can propagate in the medium. So here you can say that this value e raised to minus 1, that value is 0.368 value of E naught. So from maximum value, skin depth will give a measure of depth at which the electric field will become how much? 0.368 E naught. This is how you calculate skin depth. Okay, so that is so this is defined for a good conductor. That's why we substitute this value for alpha. Okay, so this is generally measured in millimeters. It's given in millimeters, the skin depth value. And well, I will explain this again. That is, when an electromagnetic wave is passing through a conductor, this electric field or magnetic field, that is E or H, when it travels through the conducting medium, its amplitude goes on decreasing, because in a conductor it is not lossless. As there is conductivity, there will be an attenuation. So the amplitude will go on attenuating at which value? At e raised to minus alpha z. That z is given by delta, and when the value becomes delta, z will become delta when attenuation becomes when the wave amplitude is decreased to a factor of e raised to minus 1. This e raised to minus 1 means, so it's the depth at which the wave is attenuated by e raised to minus 1. So e raised to minus 1 factor, that means amplitude is decreased to 37% of original value. So that is the significance of this factor. It's a depth at which the wave is attenuated by a factor of e raised to minus 1. That means 37% of the total value of the intensity. Okay, so that depth is given by delta. So to calculate that, what you did, for instead of E0, e raised to minus alpha z is the term. So z is delta when attenuation is e raised to minus 1. So that's what you substituted here. And you got the equation as delta is 1 by square root of pi f mu sigma. So this is a very important term. You have to know what is skin depth and you have to learn this equation. Delta is 1 divided by square root of pi f mu sigma.